Carbocation is a carbon intermediate having 3 bond pairs with carbon and a positive charge over the carbon atom. So this is a carbocation. It has 3 bond pair and positive charge over carbon. So this is a carbocation. Now we can have different kind of carbocation. This carbocation is called methyl carbocation. Similarly, if I replace one hydrogen with an alkyl group, we will have a carbocation, and this carbocation is called 1 degree carbocation. We can replace this hydrogen also with an alkyl group. So this is a 2 degree carbocation. Now similarly we can have a 3 degree carbocation if this hydrogen is replaced by an alkyl group. So this is a 3 degree carbocation. Now R can be alkyl group as well as aryl group. So R can be an alkyl or an aryl group. We can have more carbocation this carbon, that is sp2 hybridized, is called vinylic carbon. So this is a vinylic carbon and corresponding hydrogen is vinylic hydrogen. Now if I replace this hydrogen, we can put a positive charge. So corresponding carbocation is called vinylic carbocation. So this is vinylic carbocation. Similarly, we can have an allylic carbocation. Now this carbon is called allylic carbon, and the corresponding hydrogen is called allylic hydrogen. So this is allylic hydrogen. So we can replace this hydrogen with a positive charge, that is, we can replace this hydrogen and a positive charge will be there. So after removal of hydrogen, we will have this group and a positive charge over this carbon. This carbocation is called allylic carbocation. Now in case of allylic carbocation, we have a resonating structure. So allylic carbocation is resonance stabilized. So we can say in this case allylic carbocation is resonance stabilized. Similarly, we have benzylic carbocation. This position or this carbon is called benzylic carbon. Similarly, this is benzylic hydrogen. So corresponding carbocation is benzylic carbocation. So this is benzylic carbocation. And once again benzylic carbocation is resonance stabilized. So we can write resonating a structure for this carbocation. More resonating a structure can be written. So this carbocation is again resonance stabilized. We can similarly form a carbocation from acetylene. If I remove this hydrogen, in that case we will have this carbocation, and this is acetylenic carbocation. So this is coming from acetylene. Similarly, we can have a phenyl carbocation. If I remove a hydrogen from here, then corresponding carbocation will be phenyl carbocation. Now in general, hybridization of carbocation is sp2. So hybridization. So in general, hybridization of carbocation is sp2, but this is not always true. Let us see. If you see methyl carbocation, this is sp2 hybridized. 1 degree carbocation, sp2 hybridized, because it has 3 groups. 3 degree also sp2, 2 degree also sp2. So these carbocations are sp2 hybridized. Vinylic carbocation has 2 groups only. So this is sp hybridized. Now this carbocation is again sp2 hybridized because this has 3 groups. Now benzylic carbocation, it also has 3 groups, so this is sp2 hybridized. Now phenyl carbocation is also sp2 hybridized. So in most of the cases carbocation has a hybridization of sp2, but in some cases, like in this case also, this is sp hybridized, but in some cases carbocation may be sp hybridized. Next important point we have about carbocation, it has total 6 electrons. So carbocation is electron deficient species. So this is electron deficient. So carbocation can act as an electrophile. It can gain electrons. So this is electrophile. Or you can say carbocation is Lewis acid because it can gain electrons. Now let us discuss about shape. In general, carbocation is triangular planar in shape because hybridization is sp2. So this is triangular planar in shape. So we can show orbital picture. So this is the shape of a carbocation and this is triangular planar. So a nucleophile can attack from top as well as from the bottom. So nucleophile can come from the top or it can also attack from the bottom. An attack is equally likely. So attack of nucleophile is equally likely from top and bottom and bottom face. This angle is 120 degree. So these three angles are 120 degree. About magnetic nature. Carbocation does not have any unpaired electron. So it is diamagnetic in nature. So no unpaired electron. So it has 6 electrons, all are paired. So no unpaired electron. So carbocation is diamagnetic in nature. Now let us discuss stability of carbocation. So carbocation is electron deficient species. So this is electron deficient species. So any group that can donate electron will make carbocation more stable. So any electron donating group will make carbocation more stable. An electron donation can be done by plus resonance, that is, electron can be given by resonance, that is plus resonance effect. It can be given by plus inductive effect. It can also be given by plus hyperconjugation effect. So mainly carbocation can be resonance stabilized or inductive effect stabilized, or it can be stabilized by hyperconjugation. So on this basis we can decide stability of different carbocation. Let us say we have this carbocation. This is a 3 degree carbocation. And this one is a 2 degree carbocation. This is a 1 degree carbocation. And this is methyl carbocation. Now stability of these carbocation can be seen on the basis of hyperconjugation as well as on the basis of inductive effect. In this case we have 3 plus 3 6 plus 3 9 hyperconjugable hydrogen. So we have 9 hyperconjugable hydrogen. In this case we have 3 plus 3 6 hyperconjugable hydrogen. Now in this case we have 3 hyperconjugable hydrogen. Now in this case we have no hyperconjugable hydrogen. So no any hydrogen is hyperconjugable. So no any hyperconjugable hydrogen. So more the hyperconjugable hydrogen, more the stability. So we can say 3 degree carbocation is more stable than 2 degree, and this is more than 1 degree, and this is more stable than methyl carbocation. So this is increasing order of stability. Now this order of stability can also be seen on the basis of inductive effect. In this case we have 3-methyl that can stabilize this carbocation. In this case we have 2-methyl. In this case we have 1-methyl, and here we have no methyl group attached. So in this case we have maximum I effect, and in this case we have minimum I effect. Now we can write a general stability order of carbocation. This means we can have a large number of carbocation that is possible. We can decide or we can define a general stability order, and this order you have to remember. So this carbocation is most stable, and then you have 2 phenyl group, then you have 1 phenyl group, and then you have allylic carbocation, then you can have a 3-degree carbocation, and then you can have a benzyl carbocation, then you have allylic, this is your 1-degree allylic, this is a 2-degree allylic, because this carbon is connected to 2 carbon. This side we have carbon, this side we have carbon. So this is a 2-degree allylic. But now this one is 1-degree allylic. You see, this side we have hydrogen, this side we have only carbon. So this is 1-degree allylic. And this carbocation is very similar to secondary carbocation. This is more than primary. And this is more than vinylic carbocation. And vinylic is very similar to phenylic carbocation. And acetylic carbocation is least stable. Now you can remember this. This is easy to remember. Here we have 3 benzene ring, 2 benzene ring, 1 benzene ring. More the number of benzene ring, more the stability. Now the 3-degree carbocation is very similar in stability with 2-degree allylic. So this is 3-degree carbocation. So this part you can remember. 3-degree carbocation is very similar to 1-degree allylic carbocation. So 2-degree allylic carbocation. Now similarly, the acetylic is the least stable carbocation, because in this case positive charge we have on sp hybridized carbon. These are least stable because this case also we have sp hybridized. In this case we have sp2 hybridized. So these carbocations are least stable. So these carbocations are very unstable. So if possible, you try to remember this table. Another important point we have, that is aromatic carbocations are very stable. So aromatic carbocation is very stable. So sometime carbocation can be aromatic also. So this is a carbocation, but this carbocation is aromatic because it satisfies the condition of aromaticity, that is 4n plus 2 rule. So in this case, if I plug n is equals to 0, we have 2 pi electrons. So it satisfies condition of aromaticity. So we have delocalization also in this case. So it satisfies the condition of aromaticity. Similarly, we can have this carbocation. This carbocation is also aromatic. Aromatic carbocations are very stable. One more important point we have, and that is we cannot produce we cannot produce carbocation at bridgehead position. At bridgehead position. What this means, it is not possible to have this kind of carbocation. And the reason is very similar. This is sp2 hybridized. sp2 hybridized, this means shape is planar and angle is 120 degree. But the geometry at bridgehead does not allow to have a bond angle of 120 degree, and planar, it cannot be planar. So geometry does not allow. Geometry does not allow planarity as well as angle 120 degree. Both is not allowed in this case.